All right, everybody. Sorry if you hear my dogs making weird noises in the background. All right, but in this video, we're going to be talking about comparison of series. So essentially, the first one that we are going to look at is, as you can see, the direct comparison test. Now, let me try to think about this with you as we are going. It's still registering, right? It's not. It died. Maybe it did again. I don't know. All right, so if I have a series, say I have something like 1 over n squared plus 1. The sum from 1 to infinity. If I think about this, this reminds me of a p-series. A p-series because I have 1 over n squared plus 1. So that n squared kind of makes me think of a p-series. But it's not a p-series because of the plus 1. So since that plus 1 is holding me back, what I can do is say, hey, well, I think this is going to converge. I think this is going to converge because I think about the series when I have 1 to infinity of 1 over n squared. I know that that is a convergent p-series. And if I think about how this compares with my series over here, I'm pretty sure that 1 over n squared plus 1 is less than 1 over n squared as they go out forever. Now, it doesn't have to be like instantly less than. I'm going to show you a comparison later on that isn't instantly less than. But it does have to be rather quick in their series as far as like when n equals 4, n equals 5. n equals 10 is even rather quick, so we're going to infinity. So the lower the number, the better. And if it stays below, that's even better. So if I'm not sure about this, and I'm not sure that this is a true comparison, since my index is from 1 to infinity, that means if I want to kind of multiply with this inequality, I'm never going to be multiplying by a negative number. So I'm just going to straight up cross multiply. So 1 times n squared is just n squared is less than n squared plus 1 times 1 is n squared plus 1. Well, hey-oh, that's a true statement. And since that is a true statement, what that tells me is since this one is bigger, and I know this one is a convergent p-series, I don't know what I said, a convergent p-series where p equals 2, right? That means that this other one, since it's smaller, since it is less than, this must also be convergent by a direct comparison to one that I know for sure that converges right there. So that's essentially what we're going to be doing. If I want something that is divergent, then I'm going to want to show that a smaller series is divergent. That means if my series that I make up is smaller, then the unknown is bigger. If the smaller one diverges, so does the bigger one. And we will show that as well. So essentially, that's all that this beginning part is saying. If a sub n is less than b sub n, if the bigger, if the bigger one converges, so does the smaller one. If the smaller one diverges, so does the bigger one. It's not going to really matter what you call a sub n and b sub n. There is another stipulation that this has to be 0 is less than. They both need to be positive because if they go negative, it's not really going to make a difference anyways. But that's not super duper important. All right, if my air server will catch up. Come on. Hang on. All right, let's see if this is better. My air server was being really annoying. Seems like it's having better responsiveness now. All right, so determine the convergence or divergence of each series. So I'm going to introduce you to the eyeball test, downloading one item. You don't care. The eyeball test. That's not an eyeball. Eyeball test. What does my eyeball see? So what does my eyeball see? I see that I have 1 over 3 to the n here, which makes me think of a convergent geometric series. Right? And my eyeball would be correct here. That 2 plus kind of throws us off, but overall, this is going to be a convergent geometric. Let's go to the next one. Right, that's not all there is. We'll have to prove things. It's not as easy, although that would be nice. This one looks like a convergent p-series with p equals 2. My eyeball is right. This one looks like a divergent p-series where p is 1/3. My eyeball is right. This looks like a divergent geometric series with r equals 3 halves. And my eyeball is right again. All right, so just kind of looking at these things, and you will get faster at these. I'm sorry if I went too quick. But you'll start to be able to look at these things and say, hey, I think that's going to be this. I think that's going to be this because it relates to this. And most of the time, you will be able to pick it out. So that will be the case on multiple choice, things like that. Free response, we're going to have to do a little bit more work to prove these things. So the convergence of this series. So as is, it is not a series that I know, but it does remind me of a geometric that has a rate of 1/3. So I am going to compare to, I'm going to say that I'm going to let a sub n be 1 over 2 plus 3 to the n, and I'm going to choose a b sub n. This is the one that you are going to choose of 1 over 3 to the n. I would choose 1 over 3 to the n because I know that is a convergent geometric series with r equals 1/3. I don't even have to think very hard about it. If we have to do the integral test, we have to, but I like to try to stay away from it. Stick to your P series, your geometric series if you can. Those are going to be much easier for you. So the next thing I need to prove is, since I think this converges, I want the one that I made up to be bigger. So I want a sub n to be less than b sub n. So if I throw the series n, or the sequences, and I cross multiply, since I have only positive numbers, then 3 to the n is definitely going to be less than 2 plus 3 to the n. That is going to be true. So I can make my statement. This is really all the information that I needed in order to make my statement with this. So since a sub n is less than b sub n, and the series of b sub n from 1 to infinity is a, what do we say, geometric series with r equals 1/3, which is less than 1. That means it converges. That converges. The series of a sub n converges by the direct comparison test. Right, and that's it. I need all of these things. This is a big statement stating which one's bigger, which one's smaller. I also need the direct comparison test, right? That's kind of the same thing, but this allows me to use the direct comparison test and state that it converges since the other one converges. I need to state the series of b sub n. Notice I did define b sub n. It is a geometric series, and it converges because the rate is 1/3, which is less than 1, so it converges. Since all of that is true, the other series, a sub n, my original one that I actually care about, converges by the direct comparison test. All of that information is necessary. So it's less math intensive, but it is more writing intensive and proof intensive. All right, let's move on. So I said that this looks like a convergent P series. So let's pick a P series that is smaller, or sorry, bigger. So a sub n is 1 over 3n squared plus 2. And I'm going to let b sub n be 1 over 3n squared. Yeah, I could drop the 3 if I wanted to. But let's see, I want a sub n to be less than b sub n. So I want 1 over 3n squared plus 2 to be less than 1 over 3n squared. That is a true statement, but let's go ahead and cross multiply to prove it 100%. 100%! Right? So then for sure, I didn't need that 3. Right, so if you want to back up a step, you're more than welcome to. But you could have just made that 1 over n squared. Or you can make it 1 over 3n squared. Makes no difference to me. So I'm going to say since a sub n is less than b sub n, and the series from 1 to infinity, same index, of b sub n is a convergent P series with P equal to 2, which is greater than 1, the series for A sub n converges by the direct comparison test. And that's it. All right, moving on. I think this one diverges, so I want something that is bigger. So I'm going to say I'm going to let A sub n be 1 over 4 times the cube root of n minus 1. And I'm going to let B sub n, hopefully this works, 1 over 4 times the cube root of n, because that is a divergent P series where P is equal to 1/3, which is less than 1. So in this case, I want A sub n to be bigger than B sub n, since I want to diverge. If I want to diverge, the one that I pick should be smaller. If this is my series, and I think it diverges, then if I show that a smaller one diverges, then the bigger one must also diverge. That is the direct comparison test. All right, this is nice. There's absolutely no lag now. Okay, so 1 over 4 cube root of n minus 1 greater than 1 over 4 cube root of n. Let's do our cross multiplication. 4 cube root of n is greater than, for sure, 4 cube root of n minus 1, 100%. I mean, if you subtract 1 from the same thing, it's going to be less than it is. So I can say, since which way? Yeah, I have it written. A sub n greater than B sub n, and the series from the same index 1 to infinity of B sub n is a divergent P series with P equals 1/3, which is less than 1. This series, whoa, that was an ugly one. Don't do it that bad. What is that? A sub n. What is that? Yeah, is divergent. Or you could have just said diverges. That would have been faster. By the direct comparison test. And that is it for that. All right, last one we said was divergent geometric with a ratio of 3/2. So let's just compare it straight to that geometric. Right, that is my geometric. So I want A sub n to be greater than B sub n if I'm going to diverge. So 3 to the n over 2 to the n minus 1. Whoop, I just flipped it for no reason. Right, so then if I can cross multiply, since they have the same exponent with these two things, right, you can multiply in the bases. So this becomes 6 to the n is greater than 6 to the n minus 3 to the n, and that is for sure going to be true. All right, so I can say since, I don't like writing the C apparently, since A sub n is greater than B sub n, and the series for, yikes, series for B sub n a divergent, what is this? Geometric series with r equals 3/2, and I know that diverges because that is bigger than 1. Right, then I can say the series for A sub n diverges by the direct comparison test. And that is really all you guys need to show. They're not looking for a whole bunch, so it's not difficult math. The little math you need to show is just that. and then get into your proof. So really the hardest part of these is just picking which series you want to compare it with, and verifying that this comparison will work. Again, it doesn't have to work right off the bat. So like one comparison that is not as straightforward, that kind of caught me off guard the first time I really reviewed for BC. So I'm sure it'll catch you a little bit off guard the first time you're like taking BC. So 1 over n factorial is going to get really, really small really, really, really fast. Because if you think about putting in 10, that's 1 over 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Right? So super, super small number. So I don't need to compare it with anything crazy. I'm going to let a sub n be 1 over n factorial, and I'm going to let b sub n just be a normal p series, right? So p equals 2, which is greater than 1, so that will for sure converge. And if I make the comparison that what I'm really looking for is for a sub n to be less than b sub n. So this means 1 over n factorial is less than 1 over n squared. So if I multiply up, then n squared is less than n factorial. And that's not true right off the bat. So like if I put in 1 squared less than 1 factorial, that's not true. They're equal to each other. So that's no good. Well, what about 2? 4 is less than 2 factorial. That's definitely not true because that's just 2 times 1. All right, let's go to 3. Well, that's getting bigger faster, right? Over 6. Nope, that's not true either. But as soon as I get to 4, I think 4 is the breaking point, because this will become 4 squared, which is 16, less than 4 times 3 times 2 times 1. All right, so this becomes 16 is less than 24. And from this point on, so really as long as n is greater than or equal to 4, this is a good relationship. And this is a good comparison, right? This is the comparison that I have seen in all of the textbooks. This is the comparison you will see on the AP test when you take that. So this is a very good comparison to make with that P series so that this will converge, even though it doesn't happen right off the bat. So there is something to think about there. So it could be like, I don't know, I guess I could see them saying which interval is this a good comparison for, and you'd have to figure out where the break is and if it is a good comparison or not. All right, moving on to the limit comparison test. The limit comparison test is a little bit more powerful to me than the direct comparison test. It's a little bit nicer. So reason being is because essentially if we have two positive series, right, those are just positive numbers, if I take the ratio of the two, so it's like if I have 2n, one of my series is like 2n, the other is 3n, I know 2n is going to diverge, right? That's getting bigger. I know 3n is going to diverge too, but if I think about dividing the two things, right, if I make the division there, then that comes out 2/3, so they just come out as a ratio of each other. So essentially, if I can show that the limit of the division comes out a finite and positive number, means and finite is just not infinite, so just if it comes out a positive number, then both of the series either converge or diverge. So essentially whatever one I compare it to, if I compare it to like a P series that I know diverges, and I can show the limit comes out as a positive number, then I can show my original would also diverge, or vice versa, right? So let's take a look at a few example problems. So this one, just by an eyeball test, looks like it is going to converge. It looks like it's a geometric series that would converge. So I'm going to say that a sub n is 1 over 3 to the n minus 2. B sub n, since I want it to converge, I'm just going to let it be 1 over 3 to the n. So if I do the limit of the two, right, I would have, and it doesn't matter whether you do a sub n over b sub n or b sub n over a sub n. So if you forget, it's just the ratio of the two. The limit comparison test, just the ratio. So if I do 1 over 3 to the n minus 2 over 1 over 3 to the n, right, if I'm dividing fractions, I need to multiply by the reciprocal. So the limit as n approaches infinity of 3 to the n over 3 to the n minus 2. And one thing you can do is you can just multiply by 3 to the negative n, and that's fine. You could also just take L'Hopital's, because as is, this would imply, notice that's not an equal sign, this would imply infinity over infinity, which would be an indeterminate. So if I do L'Hopital's, this becomes the limit as n approaches infinity of ln of 3 times 3 to the n over ln of 3 times 3 to the n, which will simplify itself out. Those will all divide each other. So this will come out as 1, which is nice. That's all I'm looking for. I'm just looking for a finite and positive limit, which 1, pretty sure is finite. I mean, it's just one of them, and it is a positive number. So all I'm going to say is since the limit as n approaches infinity of a sub n over b sub n equals 1, and I knew the series I compared it to was 1 over 3 to the n is a convergent geometric series with r equals 1/3, and it's convergent because it's less than 1. That means that the one that I actually wanted to know about, a sub n, converges by the limit comparison tests. And that's it. That's all I need to show on that. So again, the math is not super intensive. It's just a basic limit. You do have to do L'Hopital's, but it's just a limit. It's just going to be a limit. It should be pretty simple most of the time. But the statement is the big part. This is where you guys will miss the points if you're going to miss points on these problems, is my guess. All right. So this one, what do you compare it to? Well, if I think about these things as they go to infinity, that plus 6 won't make a difference. That minus 5 won't make a difference. So if I look at the powers, I'm going to compare it to 1 over n squared. Well, what about the 2? You can put the 2 there if you want to, but really I'm just looking for my limit to come out a positive number. So I could really make that 10 if I wanted to, and it's just going to change the ratio of the numbers. It's not going to make a big difference, but I'm just going to keep it simple. So a sub n is n squared plus 6 over 2n to the 4th plus, oh, what is that, minus 5? Yeah. So if I do the limits of n approaches infinity of a sub n over b sub n, which would be times n squared over 1, and that will come out n to the 4th over 2n to the 4th. And this one, even though it would come out infinity over infinity technically, they will allow you with rationals, I believe, so with polynomials, to just state what it comes out as for the limit. You don't have to do L'Hopital's 4 times there. That would be very, very tedious. Okay, so this is really all we needed to do math-wise. Now we just need to state the things. So since the limit as n approaches infinity of a sub n over b sub n equals 1/2, which means it is finite and positive. And this series I came up with, 1 over n squared, is a convergent p-series with p equals 2, which is greater than 1. This series that I wanted to know about converges by the limit comparison test. Right. And CalcChat will not have all of this work. They will not have the justification, but I need you guys to write the justification. So please, I implore you to check out my solutions on these things. Get in there at the front of the classroom if I haven't already uploaded them online. I have not, though. I will tell you, if this is my first semester teaching BC, I have not. I'm sorry. If this is my 20th, then maybe I have, but I've probably remade these videos because I'm a terrible teacher. All right, what do you compare this one to? Well, if I take out that plus 4, so that's not going to matter. Well, if I take the square root of n squared, that's just n. times n squared would be like n to the third. So I'm going to compare it to 1 over n to the third, which is a p-series that will converge. So let's get rid of all this junk. Let's define my a sub n to be 1 over n squared, root n squared plus 4. Do I have to write that? Yes. The only other thing that I can do around that is if you want to rewrite this as n equals 1 to infinity of a sub n. Whichever one you feel like is faster, makes no difference to me, but I do need to define essentially this as a sub n some way, somehow. Alrighty. So let's see, if I do my limit as n approaches infinity of a sub n over b sub n, which would be then n cubed over 1. This can simplify to limit as n approaches infinity of the n cubed over the n squared is just going to make that n over root n squared plus 4. Hey, we've done this one before. Yeah, we definitely have done ones like these before. I know we show you at least once in AB. I know you have at least a few homework problems recently in BC on this stuff. Some of you guys have asked questions about it, so good for you. But with this one, if you try to do L'Hopital's, it's just going to flip it back and forth. This will end up on the top, and the n will end up on the bottom, the first L'Hopital's, and then you do it again and you are right back to here. So the trick with this stuff is if I multiply by 1 over n over 1 over n, and the question usually comes in at this point is, how does that help me? Well, 1 over n is the square root of 1 over n squared, which means in my denominator that I can multiply that throughout. So this can turn into 1 over root 1 plus 4 over n squared. And now as I go to infinity, that's 1, that's 1. This is going to 0. So I have 1 over 1, which is going to be a finite positive number, which is all I care about. So I can get into my statement. So since the limit as n approaches infinity of a sub n over b sub n is 1, which implies that it is finite and positive. And the one that I came up with, what was it, a p-series? Yeah, p was 3. b sub n is a convergent p-series with p equals 3, which is greater than 1. The one that I care about, a sub n, converges by the limit comparison test. That's like half cursive, half not cursive. So hopefully you listen to the words that I'm saying and not just read the words that I'm writing. But hopefully it's like close enough, right? I think. Like you can tell I wrote con, and then there's like a int. So maybe you can put together convergent and like converges. Yeah, I think it's kind of legible. All right, sorry, I'm just trying to write really fast. All right, this one, take a second, eyeball it, simplify things. I would just compare it to b sub n is 1 over n. You could also make it 2 over n. It's not going to matter. You know what, just for fun, let's make it 10 over n. Why not? Sure. Just because I feel like it. Again, that coefficient really doesn't matter. We could do 10 over 7n. Sure, why not? This is still, the point is this is still a divergent p-series. That coefficient really is not going to make a difference. It's just going to come out something different when I do my limit comparison test. So a sub n, again, I need to define. All right, so let's do my limit of a sub n over b sub n, so 2n over n squared plus 7. And this would be 7n over 10, which would give me the limit as n approaches infinity of 14n squared over 10n squared plus 70, which is still going to go to a finite and positive number of 7/5. So I will say since limit as n approaches infinity of a sub n over b sub n is 7/5, which is a finite positive number, and the series that I made up, b sub n, is a convergent p-series Oh, convergent. What are you talking about? Divergent. Holy cow. Divergent. Divergent. P-series with p equals to 1, which is why it diverges. It has to be greater than 1. Holy cow. And that tells me that the one that I care about, a sub n, diverges by the limit comparison test. Okay, so I think we've covered 7 of these things now, 7 individual tests. And I think there's only 3 more, and of those, I think only 1 is really majorly important. Maybe 2. No, 2 are majorly important. Okay. The last one's it's the root test. It's like tossed aside. They don't care about it. But you could see it, so we'll cover it. And that's all I got for this one. And I know these tests can be a lot, so please, 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 do know that in your book, I don't know if I'm there or not right now on it. I've talked about it recently. But in your book, there is a page that has, I think it's at the end of line 6. Yeah, cool. It has a summary for all of the tests. The conditions for convergence, conditions for divergence. So notice the nth term, it is only good for divergence. The telescoping can only tell us convergence. There's more that we can do with the alternating series. And there's different things we can do with remainders and things like that. But this is going to be a good page for you guys. So it's all in one page, and it has all of the requirements. So notice on that integral, it states f is continuous, positive, and decreasing. That is something you will need to state. On the direct comparison, they say that, they don't state that. Where do they do it? Oh, they state it within this, right? So the a sub n is less than b sub n, and b sub n is less than a sub n, all that good stuff. Okay, so just know that's there. Please use this stuff. My computer's going to die. I'll talk to you all guys. Bye.